So here we are in our final IDE Eclipse demo of our course. So this is where we're going to do some random access file I/O. Let's step through the code and see what's going to happen here. Well, first of all, we create an object called inout of class random access file. We do that by setting it equal to new random access file. This is the file name inout.dat, and this is the file mode read write. So we're creating this file so that we can read to it and read from it and read to it at the same time. So we're not limited to just one of those two, and we can move around randomly within the file. That's the other thing that we're going to see. We open that file assuming that it doesn't already exist, but if it does exist, that's fine. What we're going to do is set the length of the file to 0 by using the setLength method with an argument of 0. So if the file did exist already, it's like we're going to overwrite the whole thing. So we've truncated it to size 0, and we're starting over fresh. In a for loop that you see here, we use the writeInt method. So we can write whatever we want, but we've chosen to write integers. As default regular ordinary integers in Java, these are going to be 4-byte quantities, 4-byte integers, or 32-bit integers. So every time we do an inout.writeInt I, we are writing 4 bytes into our file. We're starting at the beginning of the file at offset 0, and I is going to go from 0 to 199. So we're going to write a total of 200 bytes, or 200 integers rather, out to that file. The file size then should be 800 because 200 32-bit integers are going to consume 1600 bytes worth of space, or sorry, it'll be 800 bytes worth of space because it's 200 times 4 bytes per integer. So that for loop will simply write all those integers in order into the file. Then we check the file length and print the value out, and here's where you should see that indeed the length of the file is 800 as I suggested it should be. At this point, the file pointer is at the end of the file, so we do a seek 0 to restore the file pointer to the beginning. Now that doesn't change the data that we've already written out. All 200 of those integers are still present and accounted for in the file. We haven't destroyed them. We've merely rewound the file to the beginning so we can begin reading from it. And the first thing we do is we read and write a message out containing the value of the first integer. So we do an inout.readInt, and we should read the 0, which was the first integer we wrote, and we should get this nice little message that says the first number is 0. Notice what the author does in subsequent seeks. Whenever he has a seek, he uses a number times 4. Now why do you suppose he did that? Well, given that the file pointer is always a byte pointer and measures the number of bytes from the beginning of the file, but given that he has written integers which consume 4 bytes, then you can see by using the strategy of multiplying something by 4 every time he tries to seek, that's going to ensure or guarantee that he's never going to step off the boundaries of where the integers begin and end. So when he does a inout seek 1 times 4, he's actually seeking the second integer, because 0 times 4, notice he didn't bother with the times 4 here, but he just said inout seek 0. But it's the same as 0 times 4. So when he does a 1 times 4, that's the second integer at index 1. This is actually the 10th integer, 9 times 4. So that'll be our 10th integer, and we'll read its value. In any case, as we read those values, we print appropriate messages like the first number is, the second number is, the 10th number is, and we print its value. And then we modify the 11th number. So the 11th number, I guess if we're starting at 0, the 11th number should be 10, and we're going to write over it, because after we do this operation here and we read the 9th number, the file pointer is automatically advanced to the 10th integer, but instead of the integer at index 10, which is the 11th integer, and instead of reading it, we're going to actually overwrite it with the number 555. And now we don't get a chance to actually see its value, but trust me, if you did seek back to that same position and read, you would see that the old integer has been replaced indeed with the number 555. And then we do something interesting. We seek out to the very end of the file. How do we do that? By doing a seek of inout.length. So that's going to move the file pointer right to the end of the file. And so when we do this operation right here, inout.writeInt999, that's going to write the integer 999 at the one past the end of the file. So actually the file is going to grow and it's going to be longer. Instead of containing only 800 bytes, it's going to contain 804, which is going to be then 201 integers. And we see an appropriate message printed out here that shows that. And then we're going to seek to the 11th integer. And there we go. We are going to get a chance to see the 555 because that's the 11th integer. So we're going to seek to position 10 times 4. That's where the 11th integer is stored. And then we're going to print out a message that says the 11th number is, and we're going to read it and print it, and we're going to see that 555 that we overwrote. That will not be the end of the demo because I want to show you what happens if we were to step off the boundary a little bit and seek to a place we ought not to in this context and try to do a read of what's there. We'll misinterpret because what will happen is we'll read part of one integer and part of the next integer, and those will be combined to form some other value that has nothing to do with either one of the two integers, as you're going to see. But before we do that, let's just go ahead with the demo as it is in the textbook and go ahead and run it and see what we get. So I'm running it now. It has run, and let me just scroll this back so you can see the output. So the current file length at that particular point in time was 800 bytes, as I promised you. And then we have the first number is 0, the second number is 1, the 10th number is 9. And then you remember what we did at that point in time is overwrote the 11th number, which should be the value 10 with 555. We don't see any evidence of that just yet, but that's what we did. Then we scooted out to the end of the file and wrote the number 999, making the new length of the file 4 bytes longer than it was. So it was initially an 800 byte file, but when we added that extra 4 byte integer to the end, it became an 804 byte file. Then we rewind the file pointer to the 11th position and we read the number that's there and find out that, look, it did get overwritten to 555, just like we said it would. Now, let's take a look at what happens if we were to seek to a place we shouldn't in this particular context. Now, I've prepared a little visual aid to help you understand what's going to happen in this demonstration. Over here in actually hexadecimal form, although it doesn't look like hexadecimal, but it's my intent, is these are 4 32-bit integers, each occupying 4 bytes total, and I've shown them 1 byte at a time. So this is 0, which is the first integer we wrote. This is 1 and 2 and 3. So those are the first 4 integers. What will happen is these integers will get written into the file so that those first 4 bytes are the first integer, and this is happening in that 200 iteration for loop at the beginning of the program. And then when we write the second integer, so you notice the first integer lives at offsets 0, 1, 2, and 3 in the disk file. At offset 4 is where the second integer lives. So its most significant byte goes in first, then its next, and then its next, and then its least significant byte trails at the end. And I thought I might save some time and jump ahead there. So let's say that we've already moved in those and we still have the 2 left to go. So there's our third integer, and now those are going to go obviously in these first 3 places, and boom, there they are. And then the least significant piece goes here. So what I'm showing you now is the first 4 integers, 0, 1, 2, and 3, as they will exist in that disk file starting at the beginning at offset 0, 1, 2, 3, 4, all the way to 15. Now, you'll notice that whenever the author does something with the file, he's got this times 4 that I mentioned a few times already. 9 times 4, 1 times 4, 10 times 4. And the reason he's done that, he's been very deliberate about that, so that he knows he's always going to be either at 0, 4, 8, 12, 16, and so on. In other words, he'll always be at an offset, which is a multiple of 4 bytes. Why? Because this file is supposed to contain only 4-byte integers. So let me show you what happens if we were to step off the boundaries a little bit. Let's suppose, for argument's sake, that we were to grab the byte at offset 5. We ought not to do that, right? Because that's not a multiple of 4. But nevertheless, let's go ahead and break the rules and see what happens. So offset 5 would be right here. That's offset 5 right there. And what we're going to do is we're going to position the file pointer at that spot, which again we're not supposed to be doing in this context, and we're going to go ahead and read whatever integer is there. And what do you think we're going to see? Well, obviously we're not going to see what was intended. In fact, what's going to happen here is we're going to be grabbing this byte, this byte, this byte, and this byte. And what we've got then is a copy of some bytes from one of the integers and some bytes from one of the other integers. And that is not what was intended. So we're going to have a number that, if we sort of reverse what we did before, we're going to have the 0 and then this 0 beside it, and this 1 beside that, and this 0 beside that. So in fact, that's the number that we're going to get. Now, what do you think that number is? Well, you can think of this, if you like, in a way as being a base 256 number in a sense. So this would be the 256 to the 0 column, or the ones column. This would be the 256 to the power of 1 column. This would be the 256 squared column, and the 256 to the power of 3 column. So we can go ahead and think about it that way. That makes it life easy, because then this would be basically one group of 256. That's effectively what that would be right there. So in other words, we can say that this 32-bit integer is equal to the decimal value 256. And my prediction here is that when we set the offset of the file pointer to a 5, which again, we're not really supposed to be doing that, but there's nothing that says we can't. And if we do that, then what's going to happen is, as an offset of 5, well, we're going to grab a piece of the integer from one and apart from the other, and it's not going to be what was intended, but it'll give us some value. And what we're predicting here is we're going to see the number 256 get printed off. So let's go ahead and modify the code in the demo slightly to do this and see what happens. Let's see if we really do get the number 256. So what we're going to have to do then is we'll do everything that was normally done in the demonstration. So we'll keep all the original code as it was, but then we're going to add to it some additional code. And I guess what we can do is borrow the code from here and just modify it a little bit. So let me put this in here. So we're certainly not going to do times 4. We're going to seek to this illegal position. In a sense, it's illegal. We're going to seek to position 5. And then we're going to go ahead and print what we find. It won't be the 11th number, though. Let's change this output to be appropriate. We will say the number in the cracks, because that's effectively what this is, right? We're in the crack between two integers that were in the file that were originally stored there. And we're going to go ahead and print that little message and print the value that comes. And if all is well, we should see a 256. So let's go ahead and run this demonstration and see what we get. Well, there you go. The number in the cracks is 256, and now you know why and how that happened. And that then concludes this demonstration.